In previous lecture, we studied for the Hartree-Fock equation. It is a Hartree-Fock equation. The first term of Hartree-Fock equation is kinetic energy, and it is ion interaction, electron interaction, and this one is a Pauli exclusion principle. Exclude the same spin state, and it is kind of Schrödinger equation with various electron interaction, electron ion interaction, and Pauli exclusion principle. Here we do not know that the exact value of the wave function, and we should find that this wave function. And here I will say about the Jellium model. In here, the Jellium model assumes that electron ionic distribution is uniform, and positive charge is uniformly distributed positive charge, but also electron also homogeneously distributed, and screening between electron and positive ion screens out the total potential can be considered by the zero potential because of screening of the electron and ionic potential. Therefore, in this case, the wave function can be considered a free electron extended state, and plane wave-like wave function that we call it is Jellium model. Here I will describe the Jellium model. And to solve this Hartree-Fock equation, Jellium model assumes that assumptions, and the first assumption here electrons and ions are uniformly distributed. Therefore, because of the electron ions even distribution, and the electrons is distributed, and therefore the electrons screen the potential of ions, and for example, and electronic potential plus ionic potential equal to zero because the electrons positive charge ion is screened by the negative charged electrons. And also, therefore, in this case, because the ionic potential and the electronic potential, the sum of these two potentials are zero, and only exchange term survives. Only exchange terms is survive. And the second, therefore, because of the potential, ionic and electronic potential can be screened out, and therefore we can assume that wave function is like a free electron-like wave function, and the wave function is the free electron plane wave-like wave function. It means that psi I can be write down 1 over square root v, and the exponential I k dot r is a plane wave function. And also because we should consider for the spin, because we consider in the Hartree-Fock equation we consider Pauli exclusion principle. Therefore, we should think about the spin function. And it is two spin wave functions below Fermi momentum. And this is two assumptions in Jellium model, and therefore then we should calculate this Hartree-Fock equation, and these two terms eliminated, only kinetic energy and this Pauli exclusion term. Then here it is a real space integration, and let's consider for the momentum space integration. Therefore, then we should transform from the real space to the momentum space by the Fourier transform. And here, let's do the Fourier transform of Coulomb interaction. And the Coulomb interaction is that E square over R minus R prime, and in the Fourier transform is that 4 pi E square to the dk over 2 pi cube 1 over k square exponential I k dot R minus R prime, and it is Fourier transform. And here, and because it is a Fourier transform of Coulomb interaction, and this kind of interaction can be transformed like here. And therefore, let's substitute this Coulomb interaction in the Hartree-Fock equations. And also we only consider for the exchange interaction and also kinetic energy, h bar square over 2m Laplacian psi I r and minus summation for j integral dr prime and e square over r minus r prime psi j star r prime and psi I r prime and psi j r, and the chronicle delta si sj equal to epsilon I psi I r. It is a Jellium model of Hartree-Fock equation. Because we only consider for the Fourier transform of the Coulomb interaction, and also epsilon I psi I r equal to, it is that h bar square k square over 2m psi I r and minus summation j integral dr prime and the integral dk prime over 2 pi cube and 4 pi e square over k minus k prime square and exponential I k minus k prime dot r minus r prime, and multiply the wave function psi j r prime star psi j r and psi I r prime. Then and from the r prime integration, for example here r prime integration and also this extended state and also psi j, then the summation with j, it is orthogonality, and the orthogonality say that this term, this blue line equal to 0 only survives at r equal to r prime, and only survives. it is that this term is that the crank delta r minus r prime. Then it survives only the r equal r prime, and otherwise all the terms equal to 0. Therefore, then let's write this term h bar square k square over 2m psi I r minus, and the momentum space should be below the Fermi momentum, and dk prime over 2 pi cube 4 pi e square over k minus k prime square, and also psi I, the r prime should be r, and because of the orthogonality of this delta function. Therefore, and when we calculate this one, the result from this in this one is that the energy, the dispersion relation shows that h bar square k square over 2m minus this integration can be like that 2e square over pi and the kf, and it is a functional of the k over kf. And here this term, and it is kinetic energy, and this term comes from the Pauli exclusion principle and the exchange energy. It is exchange energy effect. And even the the wave function in this case, and we assume that the wave function is free electron like plane wave case, and even though it is the wave function is plane wave, and here the energy is not only the kinetic energy, it is a free electron term, but also should consider for the exchange energy effect. Here this exact, I did not calculate exact in detail, but the exact calculation result for the f function. The f function is that 1/2 and plus 1 minus x squared over 4x, and then 1 plus x over 1 minus x. We call it is a Lindenhart function. And the Lindenhart function, then the brief functional graph of the Lindenhart function is that with x, and here it is 1, and it is fx, and the Lindenhart function is like this, and in here like this, and also it is 1. Here, when you write down the total energy of an electron in the explicit form, the total energy of an electron's system is like this: summation k. But the momentum should be lower than the Fermi momentum, and h bar square k square over 2m minus e square kf over pi, and summation of k should be below the Fermi momentum, and here it is 1 plus, because of the this Lindenhart function has the 1/2, and the 1/2 term is extracted in the outside, and then 1 minus k over kf square over 2 k k over kf and ln absolute value 1 plus k over kf and 1 minus k over kf. And when you see this, and these two is coming from the spin up and down, because there are two spin state, spin up and down, and also the summation of k should be below the Fermi momentum. And also here, and this Lindard function, and when you see that it is a 2 value, can be cancelled out by the 1/2 and 1/4 and cancel. And also, and this it is 1 means that here is the 1/2 should be included. 1/2 comes from the double counting, and because two electrons, electron 1 and 2, this interaction or this interaction is identical because electrons are indistinguishable, and therefore it is double counting should be excluded. And also because of the two spin state, we should multiply 2, and it is coming from the spin. Therefore there is no multiplying term. And the latter one is that the Lindard function. Then let's we can write down is that 2 summation over k below kf h bar square k square over 2m minus here when you multiply the kf in the numerator and denominator, e square kf over pi, and the summation for k is lower than kf, 1 plus. And here when we multiply kf square in the numerator and the denominator, it is kf square minus k square and 2k kf and ln kf plus k over kf minus k. Let's calculate the first term. And because electrons are very tiny, and extended electronic state can be considered as the not a discrete particle but a continuous wave. Therefore, it is that v over 2 pi cube and multiply 2, and the summation becomes integration. K should be lower the kf and the dk space h bar square k square over 2m. Then it is that v over 4 pi cube integration from 0 to kf. It is that because it is 4 pi k square, 4 pi k square becomes the f square k to the 4 over 2m dk, because 4 pi k square dk. And then it can be calculated, and also 4 pi cancel with each other, and h to the 4 to the h to the here. It is that because h k means here 2 pi v over 2 pi square m h bar square, and kf to the 5 Therefore, it is that V over pi square and 10 m h bar square kf to the 5. Yeah, then, and from the volume of the Fermi surface is that 4 over 3 third pi kf to the cube is that the volume of the Fermi surface, and in the volume, and the quantum, the unit cell is that the V to the 2 pi cube, then is the total number of electrons. It is total number of electrons, and here is that kf cube V over 6 pi to the square. And also we should consider for the here n prime is that the 2 spin, because of the 2 spin state, and we should multiply 2. Therefore here in the n over v is that kf square over 3 pi square because of the spin system. Spin should be included, multiply 2. Yeah, okay. Then therefore then when substitute here, when you substitute here, and it is that V equal to, when you substitute here, then it is that n over 3 h bar square kf cube divide by therefore kf square, and also 10 m. Because Fermi energy is that h bar square kf square over 2m, then therefore it is that Fermi energy and n. Yeah, it is. The first term can be calculated like this. And also I do not calculate in more detail in the second term, and here let's denote that the result. And that the result is that n, the first term is that 3/5 Fermi energy minus 3/4 e square kf over pi, and I do not exactly calculate the second term. Anyway, then when you calculate this one, it is a total energy of the n-electron system. And here, basically, the Jellium model describes the electron-electron interaction or the electron-ion interaction ignored, but only consider for the exchange interaction in the free electron model. Yes, Jellium model is like a free electron model, but the energy is not exact with a free electron case, but it is different. And also here, this is a result of the total energy of the n-electron system.